Hey there, welcome back. You sent over some really interesting research about something called rank-augmented linear attention and vision transformer. So we're taking a deep dive into that today. It sounds like it could be a pretty big deal in AI.
It really does have the potential to be significant. Vision transformers are already making waves, showing incredible skill in understanding images. The only catch is that they can be computationally expensive, especially the attention mechanism at their core.
Okay, so attention is basically how these vision transformers analyze images, kind of like how we focus on specific parts of a scene. But the standard softmax attention method gets bogged down because it's comparing every single detail in an image to every other detail. Is that right?
That's exactly it. It's accurate, but think of it like reading a whole book by meticulously comparing every single letter to every other letter. You get the information eventually, but it's a painfully slow way to do it, especially with today's high-resolution images. It creates a real bottleneck.
So that's where this linear attention comes in, right? It's like finding a shortcut to understand the image. But the research you sent indicates there's a trade off. It seems like it can be faster, but less accurate. It's producing these low rank feature maps, which I have to admit sounds a bit like technical jargon to me. Can you break that down for us?
Absolutely. Rank, in this context, refers to how much rich information is contained within a matrix. You can think of a matrix as a grid of numbers representing the image's details. The higher the rank, the more nuanced and complex the information the AI is capturing. A lower rank means the AI is getting a simplified, almost blurry version of the image, missing crucial details.
So it's like if you tried to summarize a movie just by listing the main actors, you'd miss the plot, the emotions, all those subtle elements that make it interesting.
That's a great way to think about it. And that's the problem with linear attention. It often ends up with these low rank feature maps, which means the AI isn't getting the full picture.
Okay, so that's the dilemma. We want the speed of linear attention, but without sacrificing the accuracy of softmax. Which brings us to RALA, this new rank-augmented linear attention technique, from what I understand. This is where things get really interesting.
Indeed, RALA seems to solve this problem quite ingeniously. It augments two key elements of linear attention, the KV buffer and the output features.
All right, let's start with the KV buffer. What exactly is that, and how does RALA improve it?
Think of the KV buffer as a library, where the AI stores all the information it gathers about the image. The K stands for keys, which are like labels for different image elements, and V is for values, the actual information associated with those keys.
So it's like each book value has its own Dewey Decimal Code key to help the AI find it.
Got it. So what's RALA doing differently with this library? Is it adding more books, changing the way it's organized? That's a great analogy.
Got it.
RLA doesn't add more information, but it reorganizes the existing information in a very smart way. It uses what are called context-aware rearrangement coefficients to make sure the most relevant and diverse information is readily accessible.
So it's like having a super smart librarian who knows exactly which books you need even before you ask. Instead of just listing books alphabetically, they've arranged them based on their relevance to your research topic, ensuring you get a richer understanding.
Exactly. By prioritizing information in this way, RELA essentially boosts the rank of the KV buffer, giving the AI a much more comprehensive and nuanced understanding of the image.
Okay, I'm seeing how that could lead to better performance. But you mentioned RLA also does something to the output features. What's happening there?
Even with a well-organized library, the AI still needs to be able to synthesize and analyze the information effectively. That's where the output features come in. They represent the AI's final understanding of the image. What RELA does is introduce a feature interaction strategy that makes sure these output features are also full rank and contain all the necessary complexity.
So RLA isn't just giving the AI better tools and resources, it's also teaching it to think more critically and connect the dots, like a student learning to go beyond rote memorization and actually analyze the information.
That's a fantastic way to put it. RLA pushes the AI to consider how different elements of the image relate to each other, resulting in a richer and more accurate representation.
This all sounds very promising, but does this actually translate to real-world results? How does RLA compare to existing attention mechanisms when it comes to performance?
That's the real test, isn't it? And the results are very impressive. To evaluate RALA, the researchers created a new vision transformer called RAVLT, which stands for Rank-Augmented Vision Linear Transformer.
Okay, so RAVLT is powered by RLA. What happened when they put it through its paces?
They tested it on ImageNet, which is considered the gold standard for image classification tasks. RVLT achieved an accuracy of 84.4%, which puts it right up there with some of the top performing vision transformers out there.
Wow, 84.4% accuracy on ImageNet. That's incredible. But didn't you say vision transformers are usually very computationally expensive? How does RVLT manage to achieve that level of accuracy without needing a supercomputer?
That's what makes these results even more remarkable. RDVLT achieves this high accuracy with only 26 million parameters and 4.6 gigaflops, so it's relatively lightweight and efficient compared to many other vision transformers.
So it's like having a super smart AI that can run on your laptop. Instead of needing a giant server farm, that opens up a lot of possibilities, especially for applications where resources are limited.
Precisely. This combination of high accuracy and efficiency is what makes RALA and RVLT so exciting. It's a real step forward in making vision transformers more practical for all sorts of real-world applications.
And it's not just about image classification either, right? RAVLT has been tested on other tasks as well.
Absolutely. Beyond simply identifying objects in an image, RAVLT also excels in tasks like object detection, where it needs to locate and identify specific objects, and semantic segmentation, where it labels each pixel with its corresponding category, like sky or road.
Okay, so we're talking about self-driving cars being able to navigate their surroundings accurately, or medical imaging systems analyzing scans with greater precision. This really does have wide-ranging implications.
It really does, and that versatility is another reason why this research is so compelling. It hints at the potential of this rank augmentation approach to change how we use AI to perceive and understand the world.
All of this sounds amazing, but before we get too carried away, I have to ask, did the researchers do anything to make sure these impressive results weren't just a fluke? Good science always requires a healthy dose of skepticism, right?
You're absolutely right. They conducted something called ablation studies to test RAVLT rigorously. This involves systematically removing or altering different parts of the model to see how it affects overall performance.
So it's like figuring out which ingredients in a cake recipe are essential and which ones you can tweak or leave out without ruining the final product. They're trying to pinpoint exactly what makes this RELA approach so effective.
Precisely. And the results of the ablation studies are quite interesting. They show that each element of RELA, from the KV buffer augmentation to the feature interaction strategy, contributes to the improved performance.
So there's no one magic trick, but rather a combination of factors all working together to achieve this breakthrough in efficiency and accuracy.
Exactly. What's also interesting is that the specific mathematical functions they used in RALA weren't as important as the overall principle of rank augmentation. This suggests that the approach itself is robust and could be adapted for different tasks and models.
That's fascinating. So it's not just about finding one perfect formula, but about understanding a deeper principle that can be applied across different areas of AI. This RALA approach seems to be more than just a new algorithm. It's a potential shift in how we think about AI development.
I think you've hit on a key point there. The success of RALA suggests that the rank of information might be a fundamental factor in AI performance. This opens up all sorts of new research avenues and could lead to a deeper understanding of how to build truly intelligent machines.
This is definitely some food for thought. We've covered a lot of ground today. From understanding the limitations of traditional attention mechanisms to exploring this fascinating new approach that's pushing the boundaries of what vision transformers can do. But we're not done yet.
There's still much more to explore. We've focused on the technical details so far. But in our next segment, we'll take a broader look at the implications of this research. What does this mean for other areas of AI beyond image recognition? Where could this lead us in the future? Those are the questions we'll be tackling next.
It sounds like things are about to get even more interesting. We'll be back right after this short break to delve deeper into the potential of RALA and what it could mean for the future of AI. Stay tuned.
Welcome back. We just finished unpacking the technical nuts and bolts of this new RALA approach, and it sounds like it's achieving some pretty amazing results in vision transformers. But I'm curious, is this just about image recognition, or could RALA have broader implications for other areas of AI as well?
That's a great question, and this is where things get really exciting. The research you shared focused on vision transformers for image analysis, but the core principles behind RALA could potentially be applied to other areas of AI that use attention mechanisms.
Like natural language processing. That's how AI is being used to understand and generate text, right? From chatbots to translation systems. It seems like that field is really exploding right now.
Correct.
Exactly. Natural language processing, or NLP, relies heavily on attention mechanisms. Just like vision transformers analyze images by focusing on specific parts, NLP models analyze text by attending to individual words and their relationships within a sentence or document. And just like vision transformers, these NLP models also face computational challenges. especially when dealing with large volumes of text.
So if RLA is all about improving efficiency and accuracy, by boosting the rank of information being processed, could it potentially be applied to NLP models as well? Would that mean chatbots that can hold more complex conversations? Or translation systems that can capture subtle nuances of meaning that are usually lost in translation?
Those are definitely possibilities worth exploring. Imagine a chatbot that can understand not just the words you're saying, but also the context, your emotions, and your intent. Or a translation system that can accurately convey the humor, the poetry, the soul of a text from one language to another. RLA could be a key that unlocks those next-level capabilities.
It's like we're talking about bridging the gap between human communication and machine understanding. The potential impact on global communication and cultural exchange is pretty mind-blowing.
It really is. And the applications extend even further. Think about areas like robotics, where robots need to process information from their sensors to understand their environment and make decisions. Or finance, where AI is being used to analyze massive amounts of data to detect patterns and make predictions. Anywhere you have attention mechanisms at play, our ALA could potentially bring about significant improvements in efficiency and performance.
So what we're really talking about is enhancing AI's cognitive abilities across a wide range of domains. It's not just about seeing better, it's about thinking smarter. It's like giving AI a major cognitive upgrade.
That's a fantastic way to put it. And the exciting part is that this is just the beginning. The research on RALA is still in its early stages, but the potential is enormous.
It all sounds incredibly promising, but every new technology comes with its own set of challenges. What are some of the potential hurdles or questions that researchers are still exploring with RALA?
One key area is understanding how well RLA generalizes to different types of data and tasks. The research you share showed amazing results on ImageNet, but it's important to see how it performs in other domains, with different data sets, and on more complex tasks.
So it's like making sure a new recipe works not just with one specific type of flour, but with different ingredients, baking times, and even different ovens. We need to make sure RALA is a versatile tool that can be adapted for a wide range of applications.
Exactly. Another area of ongoing research is optimization. While RLA is designed to be efficient, find the best ways to implement it on different hardware platforms, from powerful servers to low-power devices, is still a work in progress. We need to make sure RLA can run smoothly and effectively on whatever hardware is available.
So it's like tailoring a suit. You need to make adjustments for different body types and styles to ensure a perfect fit. RALA needs to be adaptable to different computational environments.
Another important area of research is interpretability. While RALA achieves high accuracy, it's also important to understand how it's making decisions. What features is it focusing on? What logic is it using? This is especially critical in areas like healthcare or finance, where transparency and explainability are essential for building trust and ensuring responsible use.
It's like the difference between getting a medical diagnosis from a doctor versus a black box. You want to understand the reasoning behind the diagnosis, not just blindly trust the output, especially when the stakes are high. Knowing how RALA is arriving at its conclusions is crucial.
You hit the nail on the head. The ability to understand and interpret RALA's decision-making process will be essential for building trust and ensuring its safe and responsible use in various applications.
We've been talking about the potential of RALA to make AI more efficient and intelligent, but it seems like this level of advancement also brings up some interesting questions about the relationship between human intelligence and artificial intelligence. Where do you see this research leading us in terms of understanding the nature of intelligence itself?
That's a profound question. I think this research is pushing us to consider how much our human way of thinking, with our ability to focus our attention and make connections, can be replicated in machines.
It's like we're trying to reverse engineer the human brain by studying how we process information and then translate those principles into algorithms. RLA seems to be a step in that direction, and it's both exciting and a little bit daunting to think about what we might discover.
I agree. And as we delve deeper into these questions, we'll likely discover new connections and possibilities that we haven't even imagined yet. The future of AI is full of potential, and RILA seems to be opening up a whole new world of possibilities.
This has been a fascinating exploration of RALA's potential. But before we wrap up, I have one last question that's been bouncing around in my head. Given that RALA is all about improving the rank of information, are there any connections to other areas of math or information theory that could further enhance this approach? Could there be other tools or concepts that we can borrow from these fields to make RALA even more powerful?
That's a fantastic question, and it's a perfect segue into our final segment, where we'll explore some intriguing connections and possibilities. That just might surprise you. We'll be back right after this short break to delve into the potential of RALA and what it could mean for the future of AI. Stay tuned.
We're back for the final part of our deep dive into RALA and its potential to revolutionize AI. Before the break, we were talking about how RALA's focus on the rank of information might connect to other fields like information theory. It sounds like there could be some really interesting links there.
There are definitely some fascinating connections to explore. Information theory provides a whole toolkit for quantifying and manipulating information, which aligns perfectly with what RALA is trying to achieve.
So instead of just talking about information in a general sense,
Yeah.
we can actually measure it, analyze it, and even optimize it using the principles of information theory.
Exactly. And there are some specific concepts from information theory that I think could be particularly relevant to RALA. For example, there's something called entropy, which measures the uncertainty or randomness of information. A high entropy signal contains more information because it's less predictable, while a low entropy signal is more predictable and therefore contains less information.
Okay, I think I'm following. So if we apply this to RLA, could we analyze the entropy of those feature maps it's creating? If the entropy is low, wouldn't that suggest that the AI is missing some of the complexity of the image?
That's a brilliant insight. By analyzing the entropy of the feature maps, we could get a sense of how much information RALA is truly capturing. If the entropy is too low, it might indicate that we need to adjust the mechanism to preserve more of the original image's richness and detail.
It's like using a microscope to examine the quality of the information being processed by RLA, making sure those feature maps aren't getting too blurry or simplified. Are there any other tools from information theory that could help us fine-tune this process?
There's another concept called mutual information, which measures how much information two variables share. We could use this to analyze how much information is being transferred from the input image to the output features in RLA. If there's a significant gap, it could point to areas where information is being lost or distorted, and that could guide us towards ways to improve the architecture or fine-tune the parameters.
So it's like having a diagnostic tool that tells us how effectively RALA is communicating information from one stage to the next. If the mutual information is high, we know things are flowing smoothly, but if it's low, there might be some bottlenecks or breakdowns in the process.
That's a great way to think about it. And this is where it gets really exciting. By applying these concepts from information theory to RALA, we might be able to unlock even greater performance gains. We could potentially optimize the entire process to ensure that information is being captured and transmitted with the highest possible fidelity.
This is mind-blowing. It feels like we're not just talking about tweaking an algorithm, but about understanding the fundamental principles of information itself. It makes me wonder if these connections could lead to entirely new approaches to AI development, beyond just improving existing models.
I think you're onto something there. The more we explore these connections between AI mathematics and information theory, the closer we get to understanding the essence of intelligence, both human and artificial. It's a journey of discovery with profound implications.
It's certainly been a fascinating journey for me. We've gone from unpacking the mechanics of RALA to pondering the future of AI and the very nature of intelligence itself. It's a fantastic example of how diving deep into a single research paper can open up a whole universe of possibilities.
I couldn't agree more. It's been a pleasure exploring these ideas with you and our listeners today.
Well, dear listeners, that concludes our deep dive into the fascinating world of RALA. We hope you've enjoyed this exploration as much as we have, and that you're leaving with a sense of wonder and excitement about the future of AI. And who knows, maybe this episode has sparked your own curiosity to explore those connections and possibilities that continue to intrigue us all. Until next time, keep those minds curious and those deep dives going.